Okay, so we're gonna do a different video today. Today we're gonna do the most hardest AP Calc questions that I could find, at least in my opinion, because everyone difficulty can be subjective. I have three of them, and I'm gonna work them out for you guys, for you to see and maybe learn something, and maybe carry that on to the AP exam that's coming up in a few weeks. Okay, so the first one, we have this clever expression. We know that this integral from 0 to infinity of kx e to the negative 2x dx has to equal 1. And the question is, what is k? Okay, so I'm seeing one thing is I see there are two variables, there's a k and an x. But one thing I do think that we can do is if we integrate this normally, we can get rid of the x's because we're going to be plugging in values. This is a definite integral. We're going to get a number. But since it's a k, which is an unknown, we're trying to find, we're going to get an expression in terms of k. And since we know that is equal to 1, we can later set that equal to 1 and solve for k. Okay, let's do that. So, okay, so let's do this. I see a kx and an e to the negative 2x. This is begging for me to use integration by parts. So I'm going to use the DI method. This is just integration by parts in disguise. It helps you like put it together easier. In my opinion, it's better than v minus v du integral stuff. I'd rather just do this. Okay, so I'm going to always differentiate the polynomial because that's usually easier to do. And I'm going to integrate the exponential, which is e to the negative 2x. Okay, let's do this. Differentiate kx, that's just k. Differentiate k, that's a constant, that's 0. Integrate e to the negative 2x. Well, we can do an easy use sum in our hands over here. And we can get negative 1/2 because we're dividing by the derivative of the inside function. And we're multiplying that by the derivative of the outside function, or the integral of the outside function, in this case, because we're going backwards. Let's repeat the process. Remember, there's a negative, so that's going to be plus 1 over 4 e to the negative 2x. Okay, so let's put this together now. This times this, it's negative here, I just wrote over the negative. So we're going to have negative 1/2 times kx times e to the negative 2x. So kx e to the negative 2x, right? And then we're going to have a minus k times this, which is plus 1/4 e to the negative 2x. So minus k times 1/4 e to the negative 2x. Okay. So now we have a function that is our antiderivative. So remember, this is a definite integral here, so we're going to plug in 0 and infinity. But math teachers, I'm sorry for putting an infinity here, because this is not really an infinity. We can't plug in an infinity. Infinity is not a number. It's something you approach. Therefore, let's use a dummy variable, let's say a, and we call this limit as a approaches infinity, because we can't use infinity. Okay, so let's do this. If I plug a 0 into this becomes 0, so that's good. If I plug a 0 into this is going to be minus, this is e to the 0 would be 1. So it's going to be minus negative k over 4. So it's going to be plus k over 4. So let's now put all the a's in so we can evaluate our limit. So limit a approaches infinity. We said this was going to be 0, so this is going to be 1. No, not 1. Okay, we're going to make the 1/2 look less ugly. K a e to the negative 2a over 2 minus k e to the negative 2a over 4. And remember, we're gonna add a k over 4. because we are going to plug in 0, which we got k over 4, as we discussed earlier. Okay, let's evaluate this limit now. As you can see, if I'm not going to write everything out, but this e can go on the back because it's a negative. That's just exponent rules. So when you imagine this e like on the bottom over here, like over here, if you imagine the e to the 2x, or 2a in this case, I plug a really big number into that. I'm going to end up dividing a smaller number, which is k. It can be any number, which probably should be small because it's an AP Calc question, by a really huge number. I'm going to get 0. Same thing here. Even though I have an a on the top, I'm still going to get 0 because that e will grow really, really quickly. So after evaluating this limit, both of these would actually go to 0. So that leaves k over 4. Okay, so now our original question was, what was k? We know that this entire integral had to equal 1. So this has to equal 1. Let's multiply both sides by 4. These two cancel out. And we get k is equal to 4. Okay, so the next one is we're going to find the interval of convergence. I just ate up the convergence, but it's really just the interval of convergence for this ugly looking Maclaurin series. No offense to the Maclaurin series, but it just looks ugly. Okay, so we're going to recall that the ratio test is when you take the limit as n approaches infinity of a sub n plus 1 over a sub n, and don't forget the absolute value of that, and you compare that to 1. If it is smaller than 1, it converges. If it's greater than 1, it diverges. If it's equal to 1, you have to do more work. So let's do this. It asks us to use ratio test, so we're going to do that. Okay, let's find our n plus 1 terms and start dividing. So we're going to take the limit as n approaches infinity of our n plus 1 term divided by our a sub n term. So that's going to be ln of n plus 1 over 3 to the n plus 1 times n plus 1, all of that cubed, times x to the n plus 1. That we're going to divide that by natural log of n over 3 to the n times n cubed times x to the n. Okay, and we're going to have to compare that and see which one is smaller than 1. What x is smaller than 1? Okay, so let's start grouping. First off, I'm going to notice that this x is not our variable interest. Our variable interest is n. So we're going to take that x out of the limit and we're going to put that there. And we're going to group all of these terms together. And we're also going to recall that when you're dividing something, we're really multiplying with the reciprocal. So I'm also going to flip everything. So let's do that. Let's see. X to the n plus 1 over x to the n, because we're dividing this time, we're flipping everything. Everything on the top goes to the bottom. Everything on the bottom goes to the top. Times the limit as n approaches infinity. Okay. Let's group the natural logs together. So we're going to have ln of n plus 1 times ln of n. Okay. So, and then we're going to multiply that by 3 to the n over 3 to the n plus 1. Then we're going to multiply that by n cubed over n, oh my god, that's an m. Okay, n plus 1 cubed. And then I think I got everything. Okay, and we're going to compare that to 1. So this simplifies just to x because of exponent rules nicely. This, okay, so let's start plugging infinities in. When I plug in infinity, if I add a 1, I ain't changing anything. It's like giving Jeff Bezos a penny. You're not changing his bank account, even though you may think that. So I'm really getting the same number back, so which is same number over same number. I'm getting 1. If I plug in infinity over this, I don't even need to plug in infinity in, because when I simplify this using exponent rules, I'm going to get a 1/3. So this would actually equal 1/3. If I plug infinity into this, it's really just an n cubed over n cubed, because that n plus 1 squared thing, when you expand this cubed polynomial, you're still gonna get that n cubed would still dominate the rest of the term. So this is gonna still be 1. If you're still confused on how this will dominate the most of the term, you can take L'Hopital's rule until you just get n cubes remaining. So like n cubed over n cubed plus yada yada yada. You can take L'Hopital's rule so many times until you get like 6 over 6, and you would get 1. If you can take it like, I think you would take it 1, 2, 3 times to get 6 over 6. Okay, so that's besides the point, but that's how the logic comes in there. So this entire limit simplifies to 1/3. So we're gonna get x. So we're gonna set, oh yeah, I also forgot, made a blunder. This is an absolute value. You don't want to do what I did. So this is an absolute value of x over 3, has to be smaller than 1. Let's multiply the 3 on both sides and then squish the x using since we have an absolute value. We need to remember that's basically just plus or minus. So if the 3 goes on that side, that's x is the absolute value of x has to be less than 3. So let's squish this now. 3 smaller than absolute value, not absolute value. Let me just took that out. Which x has to be smaller than 3. Okay, so we now find our endpoints, which is -3 and 3. But when you plug in a -3 and 3, as into x, the ratio test will fail because you're gonna get a 1. We need to do more work. Okay, so let's do more work. Okay, let's see here. So I'm gonna plug a 3 in, and I have to plug a -3 in. If I plug a -3 in into this x, I'm gonna get, so -3, this implies that Maclaurin series will look like this. N equals 0 to infinity of natural log of n over 3 to the n cubed times -3 to the n. This will actually simplify to an alternating series, which is series as n that goes to n of 0 to infinity. This is -1 to the n, natural log of n over n cubed, because these 3's go away. This converges via the alternating series test because it decreases down to 0. If that isn't obvious, well, this obviously the limit as n approaches infinity is going to be 0, because this n cubed will again dominate that natural log. There's no hope for that. And it's also going to be decreasing because n cubed is going to be positive, and it's going to be greater than that. There's no negative numbers involved. Actually, there's a negative one, but if the absolute value of that will decrease to 0. So this will actually converge. So -3 is a check. Okay, I'm sorry this cut abruptly. It's because my phone battery died, and I'm gonna have to charge it. Now I'm back. I also noticed when I was looking at the recordings is that this is barely visible. I'm just gonna rewrite that here. I'm really just saying this is -3 smaller than x smaller than 3. So that's a bad x. That's much better. -3 smaller than x smaller than 3. Okay, let's check 3 now. Okay, so let's plug this into a series, into our series, and it goes to 0 to infinity, right? And we're gonna have ln of n over 3 to the n cubed, and then we're gonna plug in 3 and we're gonna raise it to the n. Okay, 3 to the n's cancel out, and we are left with our series. Oh, that's a bad. Oh, what the hell? I'm really bad at drawing series today. The sigma symbol, I'm sorry. Series of n goes to 0 to infinity of natural log of n over n cubed. Okay, this series converges. I'm sorry if you can't see me, but this series converges. You can compare this to 1 over n squared, right? And you can multiply both sides by n over n, and you would get n over n cubed. And you're gonna find out that n itself grows much bigger than ln n, and this series does converge because it's a p series of p-value equal to 2, that's greater than 1, that converges. And since this series gets to 0 way slower than this series, and this series converges, this series has to converge too. I think that's the limit comparison test or the comparison test. They both did the same in my head, to be fair. Sorry about if you're offended by that. But this converges, so 3 is check. And I forgot to erase the part because I did record this without realizing my phone battery died. So yes, I did write it later. -3 because that's a check, which is less than it, which is equal to or less than x, which is less than or equal to 3, and that's your answer. Box it in for you already. Okay, last question. We have this differential equation, and we have that y is equal to f of t in this case, and we also have two initial conditions. Something's fishy. Yep, we have a k, and we don't know what that k is. So we need to find k in order to find f of t, and that's the original question. Also, we can't just say k something something because it was actually a multiple choice question, and k was not in any of the answers. So let's do this. Let's first solve this differential equation and see where we can get. So let's say here. Let's see. dy over dx equals ky. Let's divide y on both sides and multiply the dx on the other side. We're going to get dy over y equals k dx. Okay, time to integrate. We're going to get natural log of y has to equal to kx plus c. Okay, let's e both sides. Let me do this. Let me put this actually at the top. I'm going to e both sides, and let me write the results on the top. We're going to get y. That's going to be equal to, let's split this exponential up. We're going to get e to the kx times e to the c, which is just another constant. So we're going to get another constant, which is c2 times e to the kx. Okay, so now we have two variables we need to find. We found the original structure of f of t. We just need to find what c2 and k is. That's what the initial conditions are for. We can plug both of these things in for c2 and k, and we can solve for both. Okay, let's do this. Okay, so one thing I note is that if I plug a 0 in, this k is gone, so I can comfortably solve for c2. So let's do that. If I plug a 0 and 4 in, I'm going to get 4 is equal to c2 times e to the k times 0, which is just 0. Okay, this is simplifies to 1, exponent rules, and we know that easily that c2 is 4. Okay, now knowing that the information that this c2 is 4, I'm going to find k now. So let's do that. Let's plug in the second initial condition to find k. 12 has to be equal to c2, which in this case actually we know is 4 e to the k times x in this case, which is 2. So let's divide 4 on both sides. We're going to get 3 equals e to the 2k. We're going to natural log both sides. So both of them would get cancelled. So we can get 3, natural log of 3 has to be equal to 2k. Divide 2 on both sides. K equals natural log of 3 over 2. So let's finally write everything together. F of t will be equal to, oh, I just made a mistake. This is in terms of x, so let me quickly change that to f of x. Yep. Sorry for any confusions that I may have caused you. This is just y equals f of x, not f of t. So f of x would have to be equal to c2, which we know is 4, times e to the k, which is natural log of 3 over 2, times t. And we're done.